All right. Well, let's take another step in this chapter on potential steps, and let's take a step backwards and talk about what they call potential reversal methods. What we find, especially in electrochemistry, is that if we can somehow perturb the system in more than one way, we get more information out of the process. And so one of the ways that we do that, particularly with potential step methods, is to do what we call potential reversal methods. Let's take an example. Let's suppose our current potential curve is something like this. We can plot on our current potential curve some points of interest. We could say, let's think about a potential here that we'll call E sub f. Let's talk about a potential here we'll call E sub I. And let's talk about another potential, let's call it maybe E sub b. And now, instead of a normal chronoamperometric experiment where we do a potential step to E sub f and just monitor the current indefinitely, let's take and develop a potential step program somewhat differently. Let's say at time 0, we start with E sub I and then step it to E sub f. And that's the same exactly as we've done before. Well, let's do now potential step reversal, where at some time, let's call it tau, we step backwards to E sub b. What might we expect to see out of that experiment? Well, we actually get quite a bit of information out of the system, because now what we're going to do on the potential step back is interrogate the concentration profiles that we've developed on the step forward. The idea is that if we look at the current that flows, not necessarily as informative, but remember we'd expect to see a large spike of current and then a t to the minus 1/2 decay. Then as we step back, what's going to happen? Well, in order to answer that question, let's look at the concentration profiles. What do we expect is going to happen? Well, let's look at the bulk concentration up here. Remember, at time equals 0, the concentration in the bulk is the same as the concentration all at the electrode surface. So as x goes from 0 to infinity, at time equals 0, there's bulk concentration is all over the solution. At some time that we'll call less than tau, a concentration profile something like this, t less than tau, and that would be the case up in this region of the wave. As long as we're less than tau, what's going to happen? Well, nothing really. But if we step back, what we're going to do is interrogate this concentration profile. We're going to make the concentration go back to some value of the concentration at the electrode surface that may or may not be 0 for C sub O, but let's assume it is for the initial stage. And then we'll get a set of profiles that might look something like this, where we have successively longer times that are greater than tau. So t greater than tau, and then a little bit longer time that's t greater than tau, and a little bit longer time than that. So when we step back, we expect to see some current flow, because we're getting some reduction of the some oxidation of the C sub r that we made. So we're making C sub r here, and we're going to have then a somewhat of a t to the minus 1/2 decay of that material. So that's C sub O. C sub r, under the same condition, would look something like this. Initially, the bulk concentration of C sub r is 0 in this particular case. And so for times greater than tau, times less than tau, I should say, we get a curve like that. And then time greater than tau, we get these sorts of plots. We've made some C sub r, it starts to diffuse out into solution. Some r diffuses out into solution. Now we're reducing that r, or oxidizing that r back to 0, and so at the electrode surface, that concentration now drops, maybe to 0, maybe to some other value, but we're going to get these sort of hump-like shape of the concentration profiles out in solution. But we're going to see some current flow for that reoxidation process, and that's what we're seeing on this curve. Question is, how can we, well, this is kind of interesting because it allows us to ask ourselves the question, or allows us to answer the question, what's happening to R? Once we made R from O, what's happening to R now? All right, maybe R is involved in chemical reaction, maybe R is it's got a change in diffusion coefficient, so we can tell about R by doing that reverse step, get some information that we really don't have if we do a single step. How do we solve this type of problem? Well, the first part, up to tau, is the same as always, just like we've already solved. So the problem is after tau. And the way to do that, that's efficiently, is what they call the zero, use the zero shift theorem. In the initial conditions, we'll write out a special equation they call the zero shift theorem, which in the book is S sub k as a function of time is equal to 0 for all times less than k, and S sub k t is equal to 1 for all times greater than and equal to k. So if we plot our function S sub k, it just steps from 0 to 1 at some time k. And so we can think of our zero shift theorem as an electrochemical, as a switch in our theory. We can put this in, do a switching sort of function. So what we're going to do is switch from the forward to the back system by putting in this zero shift theorem. Let's see how that works out. The book has a longer discourse, especially in the back, about the zero shift theorem, but we'll kind of briefly go over it a little bit. So for example, what we would do for our conditions with the potential reversal step is say, well, the E as a function of time is equal to the E final plus S, and K in this case is tau, because tau is where we said we did this switch. And it would switch between EB minus and EF. So when S sub tau is equal to 0, this whole function is 0, and so E sub t would be equal to E sub f, and that would be the first part of the step. And then when it switches to 1, then E sub f gets canceled out, and then we've got E sub b in the equation. Now the advantage of using the step function is that when we do the Laplace transform of the step function, we get a nice exponential function out of the Laplace transform. So Laplace transform of the step function is when we think about this sort of a equation, well, we've introduced our step function times the function that we're really interested in as a function of time. We get this exponential function minus e to the minus ks. K again is our time that we do the stepping, and our Laplace function of time that we originally are interested in. And so that allows a fairly straightforward inclusion of the step function in our Laplace thing. And the book goes through the whole slew of solutions. I'm not going to worry about that. It's the solution is fairly involved, but it's not any more tricky than the other ones. So I'm just going to write down the results. For a Cottrell equation type experiment, it's not a Cottrell system exactly, because in a Cottrell we just step forward. In this case, we're going to step backwards, and what I'm talking about with a Cottrell type step is that we're going to step out to the limiting plateau, and then we're going to step back to a point in which we'd essentially be at the limiting plateau for the oxidation of R. In other words, if we thought about this as being a reduction, or an oxidation rather than a reduction, this would be the limiting plateau for the reduction or oxidation of R. So it's Cottrell-like in that way, that we're stepping out to that limiting plateau. In other words, we don't consider a potential dependence in this result, and we don't consider a time dependence in this result. IF is equal to the Cottrell equation, as you'd expect. Can't be any different. So in other words, the current on the forward part of the step is I sub f. On the reverse step, for t greater than tau, it's t less than tau, we get minus IR as a function of t is equal to NF, I'm not writing that very clearly, but NFA d0 to the 1/2. So far it looks like the Cottrell equation. Pi to the 1/2. And then this bracketed term, which includes the time dependence. And this basically starts the clock at time equal to tau for the plotting. So you can, if you think about that, we're just sort of shifting everything over by tau amount when we're doing that plot for the reverse step, and essentially setting that equal to 0 and then going forward from there. So it looks complicated, but it's not really any more complicated than the forward one. So the forward and the reverse, all we're doing there is changing the shape of the wave. And then if we do something like plot the reverse current as a function of time over the forward current, we get this result. Now, what do you mean by that? Well, what we're meaning by that is that we've got this sort of experiment where we're stepping out and then we're stepping back. And so TF would be, if we measure at any particular time, and then we'd consider the same time after that particular time, or some time after that. So this would be T sub f, and this would be T sub r. We could plug those in to the equation and get the ratio of the current on the reverse step to the current over the forward step. So in other words, T sub f is the time from 0 to that point somewhere on the forward step, and T sub r is the time after 0 somewhere on the reverse step. And the ratio of currents as a function of the times that we've put in, TF and TR, is given by this form of the equation. You can get that just by taking these two equations and putting them together. And a particular interesting case is when T sub r minus tau is equal to T sub f. In other words, T sub f after 0 is the same amount of time as T sub r is after tau. Same length of time from the initial step to the step back. At that point, when that's the case, we get, and you can easily verify this, expression like this, 1 minus 1 over tau over 2 tau to the 1/2. In other words, T sub f would be equal to tau in that case. This stupid pen, they can't write very well. Let's try that again. So T sub f is equal to tau, T sub r equal to 2 tau. All right, and under these conditions, I should have made that condition clear. Under both of those conditions, we get this result. In other words, as soon as we get to TF, we measure the current, and then we step to the back potential and make a measurement at T sub r, and so on. In other words, that ratio of the reverse to the forward is 0.293 under those conditions. So again, let me just clarify that. I think I've done a bad job about that. So if we do a step to the forward case, step back, not necessarily back to the same point that we started from, but maintaining this Cottrell type situation, this would be tau. It also would be T sub f. And then this same amount of time would be 2 tau. And that would be T sub r. We would get this special case of equal to 0.293. Now, you might initially expect we'd get exactly the same amount of current on the reverse step as we get on the forward step. If we go back and look at our curves here, you can see why we don't. These are not exact, but they do give you a pretty good idea what's going on. On the reverse step, even though we're going to get some of the current flow, we still don't get all of the current that is required. First of all, the gradient isn't the same at the interface because it's not, the bulk concentration of R wasn't the same as C sub O in the first place. And so we never get an equivalent of the bulk concentration of O as in R. They're just not the same. Also, some of the R species never gets back to the electrode surface. Since it can diffuse either way, it can easily diffuse away from the electrode surface rather than to the electrode surface. And there's no real net gradient pulling it towards the electrode surface. It's going to diffuse either way because there's essentially 0 R out in the solution, and it could or could not be 0 at the electrode interface. In this case, it would be. So a lot of the material is lost out into the solution. So that's what we're getting there. Because we don't have the same initial conditions for O and R, we also lose some of the material.